So in today's lecture we are going to discuss the experimental determination of rate laws. What are the techniques of determining the rate laws? Okay. So in today's lecture we are going to do a lot of problem solving as well, and the problems will start going to the they will increase the level of the problem. Okay. Till now we are doing some basic elementary problem, we also saw some JEE advanced as well as mains level question, but in today's lecture the level of the questions will again rise a little bit. So okay, I hope everyone is having a notebook with him, and whatever we are doing in the class they are making a parallel notes with in his copy, and I hope things are getting easy for you and you are getting accustomed to the platform and you are able to prepare with us effectively. Okay, so let's get started. So in today's lecture we are going to analyze some of the most important first order reactions. Okay, so basically there is a technique called direct or indirect estimation of reactants. Okay, now how we'll do these things in the lab. Okay, the main question that comes in, whatever theory which we are reading right now, okay, theories are little easier to understand, but at the experimental level things become really difficult. So whenever we are saying that a reaction is say first order, second order, we have obviously determined those things in the laboratory. So what exactly we do there is, suppose we are carrying out a reaction. Okay, suppose we are reacting some reactant, or there is one reactant that is reacting in a reaction. Suppose it is a decomposition reaction, hydrolysis reaction, it can be anything. Now when the reaction is happening, what we will do is, after certain interval of time we will stop the reaction and we will take some quantity out of the reaction mixture, and we will analyze that quantity of the mixture so that we will be able to understand how much reaction has been completed till now. Okay, let us take an example to understand. Suppose that I am carrying a reaction, say I am decomposing any substance, say calcium carbonate I am decomposing into calcium oxide and CO2. Okay, this is just an hypothetical example. So suppose we started this reaction. Okay, so we know that at time t equals to 0 there was only calcium carbonate that was present. Okay, now say after 2 minutes, okay, I started heating it, say after 2 minutes I will take out some substance from the reaction mixture and I will analyze that particular component. Okay, so I will take out some component from the reaction mixture after certain interval of time and I will analyze it. So by analyzing I can understand how much calcium carbonate is still left. Okay, so whatever be the calcium carbonate in that small sample, we can calculate the calcium carbonate left in the in the reaction mixture. So we will get to know the amount of calcium carbonate that is present. We knew that how much calcium carbonate we started with, so we will know that how much amount has reacted after a certain interval of time. Then we will keep on doing this thing. After regular interval we are going to take out some the component from the reaction mixture. So we are going to take say 5 ml of it, we are going to do some reactions or do some tests so that we are able to understand how much component is left. Okay, so this is how we do it experimentally. Okay, so let us understand with an example. Say suppose let us take an example of decomposition of H2O2. Now I have already told you when we were doing the first order reaction, this is an example of a first order reaction. So we know that H2O2 decomposes into H2O plus O2. Okay, so how we will analyze this mixture? Okay, suppose we have taken a beaker, okay, and we are decomposing H2O2 in it. Okay, so we have say taken some amount of H2O2. Now we know that this is decomposing. Suppose it is decomposing on heating, so we are heating this. Okay, we are increasing the temperature. Now this has started to decompose. So at time t equals to 0, when the reaction didn't start, we will know that only H2O2 is present. Say after 5 minutes, okay, say after 5 minutes I analyze the reaction mixture. Now how I will analyze the reaction mixture? I will take some amount of this, okay, I will take some amount of the reaction mixture and I will analyze it separately. Now we know that H2O2 is a oxidizing as well as a reducing agent. Okay, So what we can do is, the portion which we have taken out, because it has both oxidizing as well as reducing character, so it can easily undergo a redox titration. Okay. So we are going to take out say 5 ml of this reaction mixture after say 5 minutes. Now we will titrate that 5 ml of the reaction mixture which we have taken outside with say KMnO4, acidified KMnO4 or acidified potassium dichromate. So basically acidified KMnO4 is a very strong oxidizing agent. So in that case, when we are titrating the volume that we have taken out from the reaction mixture with KMnO4, we know that KMnO4 is a strong oxidizing agent, so it will cause the oxidation of that particular component, that particular volume of H2O2. Okay. So what we are going to say is, say after time t equals to 0, we are having initial amount of H2O2 as A. Say after some time t, let the x be the extent of reaction per mole. So the amount reacted would be 2x, so we will be left with A minus 2x. Okay, and at that time we will know that 2x amount of H2O and x amount of water would be formed. Okay, so this is the basic stoichiometry. So what I am going to do, I am going to periodically take out, say after 2 minutes, 4 minutes, 6 minutes, periodically I am going to take out some portion of the reaction mixture, and that reaction mixture we know it would definitely have H2O2 in it, and we will titrate that particular, okay, the particular portion which we are taking from the solution against KMnO4. KMnO4 being a strong oxidizing agent will oxidize H2O2. Okay. So H2O2 in that case would behave as a reducing agent and KMnO4 would behave as a oxidizing agent. So we say that H2O2 is titrated against KMnO4 or K2Cr2O7 in acidic medium at different interval of time. Okay. So through these titration, through the amount of KMnO4 used, we will be able to understand how much H2O2 is there in the solution. Okay. So let me take a example for this now. So now suppose we are taking KMnO4 in acidic medium. Okay, we are titrating it with the H2O2. Okay, we are not titrating with the entire amount of H2O2 that was present in the reaction. So the reaction, we have started the reaction, and after some interval of time we are taking out some portion of the reaction mixture outside and we are titrating it with H2O2. Okay. So we know that whenever we are titrating a oxidizing agent with a reducing agent, we will say that number of equivalents of KMnO4 should be equal to number of equivalents of H2O2. Okay. So this is the basic of a redox concept that we are going to use. Okay. So basically we will say that the portion which we have taken out, it contains certain amount of H2O2. Okay. So the H2O2 that was present there, so number of H2O2, number of equivalent of H2O2 that was present there, if we titrate with KMnO4, it will consume same number of equivalent of KMnO4. So we will write number of equivalent of KMnO4 as, suppose N is the normality of KMnO4, V is the volume of KMnO4. Okay. And suppose we know that X is the moles of H2O2, okay, or A is the moles of H2O2 into its N factor. Okay. So the N factor is 2. So basically we will say that because we are titrating with a known solution of KMnO4, so its normality would be constant. So this is also constant. So we will say that X is proportional to the volume of KMnO4 used. Okay. So basically what we are going to say now, the amount of H2O2 that is present in the given solution will always be proportional to the volume of KMnO4 that it is consuming. Okay. So I hope this is clear to you. So basically what we are saying, we are taking H2O2, now this is decomposing into H2O plus O2. Okay. So what I am saying, we will start this reaction. Now we know that at time t equals to 0, we are having only H2O2. So suppose we are having its A moles. After say some time t, when x mole of this has reacted, so leftover will be A minus 2x and H2O form will be x and this will be formed as x. Okay. So after every after every time interval, I will keep on taking out the solution from the main reaction mixture and I am going to titrate it with KMnO4. Okay. So, the volume of KMnO4 consumed by that portion would be proportional to the amount of H2O2 that is present in the solution. Okay. So, suppose V0 is the volume of KMnO4 used at time t equals to 0, okay, and Vt with the volume of KMnO4 used at time t. Okay. So, what we are going to say over here? Okay. So, I hope this step is clear to you. Okay. So, basically we are saying that 2H2O2 is breaking into 2H2O plus O2. Okay. So, V0 I have already told you is the volume of KMnO4 consumed at time t equals to 0. Okay, and Vt will be the volume of KMnO4 consumed at time t. Okay. So, at time t equals to 0, only H2O2 was present in the solution. So, whatever volume of KMnO4 we are using, it will titrate the entire H2O2. So, that volume would correspond to the initial concentration of H2O2. So, we will say that volume V0 is proportional to the amount of H2O2 present. Okay. So, this is basically our A0. Okay. So, at time t equals to 0, when we are titrating the reaction mixture, because at time t equals to 0 there is only H2O2 present. So, whatever volume of KMnO4 we are adding, that will completely consume the entire H2O2. So, we will say that at time t equals to 0, volume of KMnO4 consumed will be proportional to the amount of H2O2 present. Okay. Say after some time t, we have taken out some portion of the reaction mixture and we are titrating it with KMnO4. So, the volume of KMnO4 consumed by that particular portion will be proportional to the amount of H2O2 that is left after time t. Okay, because some of the H2O2 might have decomposed through this reaction. Suppose at time t is equals to 5 minutes, some of the H2O2 has already broken down into H2O and O2, some amount would be left. So, whatever amount is left at that time, it will be titrated against KMnO4. So, Vt would correspond to the amount of H2O2 present at time t. Okay. So, we can easily say that we know that because it is a first order kinetic, so we can write the kinetic equation as 2.303 log of base 10. Now, we know that the initial concentration was proportional to V0 and the final concentration is proportional to Vt. Okay. So, this will be the equation. So, we will directly put the value of V0 and Vt and we can get the value of rate constant. Okay. So, I hope this is clear to everyone. You can write this down. So, this is how we do it experimentally. Whenever we are doing a reaction in lab, we will after some time what we will do, we will obviously keep on removing or we will keep on taking out some portion of that reaction mixture, and whatever portion we have taken it out, we will react or titrate with something else, so that we get to know the amount that is left. Okay. So, that we can get the amount of substance left at that time. Okay. So, I hope this is clear to everyone. You can write it down quickly. Now, the second example is decomposition of NH4NO2. Now, we know that NH4NO2 is a solid. On decomposing it gives H2O plus N2 gas. Now, in the case of H2O2, we were estimating the reactants. We are directly estimating the reactant, we are calculating the concentration of reactant based upon the volume of KMnO4 it is consuming. In this case, what we will do, because we are having a gas N2, so we will record its volume. Okay. So basically the rate of this reaction was determined by measuring the volume of N2 evolved at different time. Okay. So say at time t equals to 0, okay, at time t is equals to 0, suppose this had A moles, after say some time t x mole reacted, so basically we are left with A minus x and we will form 2x and we will form x moles of N2. We know that because it is a first order reaction, first order reactions are completed in infinite time. So at time t is equals to infinity, we will assume that the reaction has gone for completion. So the moles of N2 formed would be A. Okay. So what we are going to do, we are going to measure the volume of N2 after every interval of time. Okay. At time t is equals to 0, volume of N2 evolved would be 0 because only reactant would be present. After say time 5 minutes, some volume of N2 would be evolved out. So we know that PV is equals to nRT, reaction is carried out in a constant, under a constant pressure. So basically we will say that volume pressure is constant, temperature is constant, R is constant. So number of moles of N2 would be proportional to its volume. So we will directly say that if V0 is the, if Vt is the volume of N2 evolved at time t and V infinity is the volume of N2 evolved at time t is equals to infinity. Okay. So we will say that V0 is proportional, Vt will be proportional to x. Okay, we are recording the volume say after 5 minutes. So 5 minutes, depending upon the number of moles of N2 formed, it would correspond to that particular volume. So the volume at time t would be proportional to the amount of N2 that is present there. Now amount of N2 is also equal to the amount of NH4NO2 that has reacted. So we will say that amount of NH4NO2 reacted is also proportional to the volume of N2 evolved at time t. Okay. Now at time t is equals to infinity, when the reaction is complete, we know that the entire reactant has converted into product. So the volume of N2 recorded at that time would correspond to its mole, that is A, which was also the initial concentration of the reactant. So basically V infinity would correspond as to A. Okay. So we will say that amount of NH4NO2 present initially is proportional to V infinity. Okay. So we will say that amount of NH4NO2 present initially was A0, this is x. So we know that A minus x will be proportional to V infinity minus Vt. Okay. So we will directly write the equation. We will say that Kt is equals to 2.303 log of A, that was initial amount of NH4N2 divided by AT. AT is A minus x, which is V infinity minus Vt. Okay. So suppose a data has been given to you, say at time t is equals to 5 minute volume N2 evolved, at time t is equals to 10 minute volume of N2 evolved, at time t is equals to 15 minutes volume of N2 evolved, at time t is equals to infinity volume of N2 evolved. So what we will do, we will use this equation, we will calculate the value of rate constant at different time interval, that is at 5 minutes, 10 minutes and 15 minutes. If the value of the rate constant using the first order equations comes out to be same, it means that it is a first order reaction. Okay. So this is the direct estimation of a product. We are directly estimating the product. Through the estimation of product, we are coming to know about the initial amount of NH4NO2 and the amount of NH4NO2 that has reacted in the reaction. Okay. So this is the expression. Okay. So I hope this is clear to everyone. So this is how we do it experimentally. Okay. We carry out a reaction in lab. After some time, say 5 minutes, 10 minutes, 15 minutes, we periodically take out the portion of the reaction mixture and we analyze it. We can either analyze it through titration or through measuring its pressure, through measuring its volume. Okay? So that is how direct or indirect estimation works. This is the estimation of product. Okay? So let us solve this question. Now this says that in an experiment on the decomposition of aqueous NH4NO2 at a certain temperature, the volume of N2 gas collected at different time interval was as follows. Okay? So we know that we have already done this expression now. We know that Kt is equals to 2.303 log of V infinity upon V infinity minus Vt. Okay? So you can have any equation over here. Okay? It is decomposing to give some gas. Okay? So depending upon the data given, you can derive the first order kinetics equation. Okay? And you can prove whether it is first order kinetics reaction or not. So basically what we have to do, we have to calculate the value of K, say at 1190 seconds. So that would be 2.303 upon 1190 into log base 10. V infinity was 9.5 minus, like volume at that time was 5 ml. Okay? So this will be the value of rate constant at time 1190 seconds, and at 2300 second the volume of N2 evolved was 7.3. Okay? So V infinity is again 9.5. So this is 9.5 minus 7.3. So in this way you can calculate the value of rate constant at different time. If you will calculate this, you will get the same value of rate constant, indicating that it is a first order reaction. Okay? Just have a quick look on the reaction on the question, and you can have a quick look at the solution as well. Okay? So if you look what we are trying to do exactly, we are not following the pattern of solving only objective questions. Okay? The most common mistake that the student makes while preparing for JEE examination is they basically solve only objective question, and they are trained in a manner that they want to solve only objective question. It might help you at that point of time, but it is a very dangerous process to follow. You have to understand the topic, you have to go in the detail of that chapter, you have to do a lot of subjective solving, because subjective solving helps you in lot of engagement. You get engaged with the formula, you have to carry a lot of calculations, so you have to work on many skills at the same time. While with objective solving, the data are generally given in such a manner that they are easy to calculate. So you don't have to think much. Basically, a subjective solving will help you in developing a good analytical power, and that is what is required for examinations like JEE Mains or Advanced. Okay? You have to read a topic as if you are doing a research on it. You don't have to do it in the manner that you just want to get marks in that particular topic. You have to do it that this is just for the love of that particular chapter. If you love that particular chapter, if you are enjoying the particular chapter, then there is no limit of solving. You can solve anything and everything. But make sure that the process is correct. You are doing a good amount of objective as well as subjective solving. Even if you are appearing for NEET or you are appearing for JEE, it doesn't matter. Because if a student is solving a lot of subjective question, his overall skills will definitely increase. And that is how like toppers are created. They are not created by cramming the objective questions or memorizing the formulas. They practice a lot and at the subjective level, because subjective approach opens up the mind very effectively, and the skills are altogether different for a student who is doing a objective or for a subjective solving. Okay, so I hope you are doing the subjective solving. That is why I am giving more of, like, every DRS is roughly having 5 subjective questions every day. So ensure that you are solving at least 5 to 6 subjective questions every day. There are books from where you can do a objective solving, but once you are clear with all the concept, all the data crunching, all the data structures, then it will become very easy. Like, what I would suggest over here is, if you look at a subjective question, subjective questions are generally long, so it takes a lot of time to read. Okay, when it takes a lot of time to read, it engages you a lot, and that is what I am looking for. Engagement, real time engagement with the problem. Now what happens in an objective question, they are very short. So you read it, you extract the data and you just solve it. But in a subjective approach, you have to keep on looking at the data, you have to keep on understanding the language of the question, and then you can answer it properly. So if that skill is generated, then solving an objective question becomes a very easy task. And believe me, through this process, you will see after 2 or 3 months, you will see that you are able to crack even the toughest level of chemistry problem very easily. Okay? So I hope this example is clear to everyone. Now just look at this question, just read it. So there is basically a reaction of dehydration of oxalic acid by conc H2SO4. Oxalic acid is breaking into CO plus CO2 plus water. Okay? So this question says that 2 ml of the solution was withdrawn at different time. Okay? So I am saying that only we are taking a oxalic acid, we are adding H2SO4 to it. So we have started the reaction. What we are doing, after every say a particular time, we are removing 2 ml of the solution. So we will analyze that 2 ml of the solution. From that 2 ml of the solution, we will come to know how much oxalic acid is left after certain interval of time. Okay, and through that we are going to analyze the reaction mixture. So basically 2 ml of the solution was withdrawn at different times and titrated against 0.1 normal KMnO4 solution, so that the reaction is of the first order and the data has been given to you. Okay. So what is basically KMnO4 doing? We know that a KMnO4 is a very strong oxidizing agent. Okay. So basically KMnO4 and oxalate ion would undergo oxidation reduction reaction. So we know that oxalate would be breaking into CO2 and 2 electron, whereas KMnO4 would be changing into Mn2 plus. Okay, so this is the idea from redox. Even if you don't know the idea of redox, still you can answer this question. Okay, so basically we know that whenever we are adding KMnO4, so basically it is titrating the oxalic acid. So after every particular time, whenever you are taking 2 ml of it, and when you are titrating with KMnO4, at that instant you are coming to know about the amount of oxalic acid that is present at that particular time. Okay, because say there was 10 moles of oxalic acid initially, after say 10 seconds 8 moles were left. So we are taking out some amount is withdrawn from the reaction mixture, we are titrating with KMnO4. So the amount of KMnO4 that it is consuming will tell us the amount of oxalic acid that is present in that 2 ml sample. Now whatever is present in that, so that is the amount of oxalic acid left in the main reaction mixture. Okay, so we will say that number of equivalent of KMnO4 is equal to number of equivalent of oxalic acid. Okay, so n factor of KMnO4, we know that it is 5. Suppose its normality is m, say volume consumed is V. Number of equivalent of oxalic acid would be number of moles. Suppose the number of moles is A into its n factor, that is 2. So molarity n factors are constant because we are titrating it against a fixed quantity, fixed concentration of KMnO4. So we will say that A, that is number of moles of oxalic acid, is proportional to volume of KMnO4 it is consuming. Okay. So at time t is equals to 0, say V0 is the volume of KMnO4, okay, consumed. So at time t is equals to 0, we know that only oxalic acid would be there. So whatever KMnO4 we are adding, it is titrating all the oxalic acid that is present in the initial mixture. So we will say that V0 is proportional to the amount of oxalic acid present initially. Okay. So I hope this is clear to everyone, because data that has been given to us is at time t is equals to 0 minute and at different time interval. Okay. Say after time t, now Vt is the volume of KMnO4. Now when we are titrating it after time t, some oxalic acid have already reacted in this reaction. Okay. So whatever is the leftover oxalic acid, that would be titrated with KMnO4. So basically Vt would correspond to the amount of oxalic acid left. Okay. So I hope this is clear to everyone. So this is the, and this is one data. Okay. So we know that the initial amount was A naught and the amount of oxalic acid left is say A naught minus X. Okay. Suppose it was A initially, X reacted, so leftover would be A minus X. So we know that the KT is equals to 2.303 log of A naught. So A naught is proportional to initial volume of KMnO4 divided by A minus X proportional to the volume of KMnO4 at different time t. Okay. So just what we'll do, we'll take V naught as 22, at 300 minute we'll take the value of Vt as 17, time is 300, so we'll calculate the value of K. Similarly, we'll do this for this data as well. So time is 450 minutes and Vt is 15, V naught is still 22. Okay. We'll calculate the value of K. At time 600 minute, so when t is 600, Vt would be 13.4. So we'll again calculate the value of K. If the rate constant using the first order reaction comes out to be same, it indicates that this reaction is following first order kinetics. Okay. So I hope this is clear to you. So just look at the step what we are doing. So basically an idea of redox is quite relevant over here. Now JEE will obviously ask such kind of question only where they are trying to incorporate concepts of two chapter. Okay. It's never like a JEE will simply ask a question on a formula. They basically try to make a blend of different chapters. Redox, I have already told you, redox, ionic equilibrium and a few portion of gaseous state and stoichiometry. They will be used everywhere in all the chapters. So you need to be very sure about these chapters. If you have not done some of the chapters in a proper manner, so I would suggest you just start revising your previous notes whatever you made. If you are having any problem in ionic equilibrium, you can go in the catch up videos and you can start doing at least the ionic equilibrium videos. I have already made 6 videos, 6 lectures I have already delivered for the ionic equilibrium revision. So you can have a look at that because we are going to use it exhaustively in solid state solutions as well as electrochemistry. Okay. So I hope this question is clear to everyone. Now let us look at this question. Now this question says that for any acid catalyzed reaction A changing into B, so this reaction is basically catalyzed by H plus, half-life time period is independent of concentration of A. So basically we know that yesterday we have already done that T half is proportional to concentration raised to power n minus 1. So it is independent, it means that n is equals to 1. Okay, so we can say that the order with respect to A is 1. Okay. We don't know about H plus, so we will calculate the order with respect to H plus. So it says that at definite concentration of A, definite concentration means this concentration is constant. Okay. So the half-life time period is 10 minutes at pH equals to 2. So when we are taking a definite concentration, that means this is a constant, constant multiplied by a constant is another constant. So this is rate is equals to K dash into concentration of H plus raised to power 5. So this is a yth order reaction. So we know that half-life time period is proportional to A raised to power 1 minus n. In this case it is H plus raised to power 1 minus n. Okay. So initially the half-life time period was 10 at pH 2. So this is 10, H plus is 10 raised to power minus 2 raised to power 1 minus n. Okay. And when the half-life is 100 minute, so this is 3, so that is 10 raised to power minus 3 raised to power 1 minus n. So just divide the two, so we will get this as 1 by 10, this will be equal to 1 by 10 raised to power 1 minus n. Okay. So this says that definite concentration of A half-life is 10 minutes. So 10 is proportional to H plus raised to power 1 minus n or 1 minus y you can say. Okay. So 10 will be proportional to 10 raised to power minus 2 raised to power 1 minus n. Similarly 100 will be proportional to 10 raised to power minus 3 upon 1 minus n. So you can calculate the order of this reaction. Okay. So when you divide this, so it becomes 1 by 10. Okay. and this becomes 10, sorry. Okay, so this becomes 10. So basically we will say that 10 raised to minus 1 is equals to 10 raised to 1 minus n. So 1 minus n is equals to minus 1. So n will be equal to 2. So order with respect to h plus is n, that is y in this case. So the value of y is 2. So the rate equation will be x is 1, y is 2, x plus y would be 3. Okay. So I hope this is clear to everyone. So basically you have to read the question properly. There are a lot of things that is directly given in the question only. Because it was saying that time period is independent of concentration of A, it means that it is first order with respect to A. Now at definite concentration means that this is concentration is constant. So constant into constant is a constant. So we are replacing it with a constant K dash. So the order with respect to Y is, with respect to H plus is Y. So we will say that half-life time period is proportional to concentration of H plus raised to power 1 minus Y, or you can write as 1 minus n, where n and y are the same thing, that is the order with respect to H plus. So on taking the ratio we will be able to find out the value of Y. So we will say that the value of x plus y is 3. Okay. So I hope this is clear to everyone. Okay. Now let us understand what is a pseudo first order reactions. Okay. Basically pseudo means false. So they are basically false first order reaction. Now what do you mean by a false first order reaction? Now there are reactions that have higher order, but they are found to behave as first order and are called as a pseudo first order reaction. Let us take an example to understand. Suppose we are having ester. Okay, suppose we are having a ester, say we are having a methyl. Suppose we are having a methyl ester. Okay. So we are having a methyl, we can name this as methyl ethanoate, and we are doing its hydrolysis. Okay. So basically the hydrolysis of this is done in the acidic medium. So on hydrolysis this will give us acid plus alcohol. Okay. So if you don't know this reaction, don't worry, reactions will be given to you. Anyways, we are going to cover this in organic chemistry when we are going to understand the mechanism of this. So basically if you look at this reaction, okay, there are two products that are involved over here, acid like the ester and the water. So I can write the rate as K into concentration of ester into concentration of water. Okay. Now if we are carrying out the hydrolysis of ester in water, okay, so obviously water will be behaving as a solvent. So suppose we take 0.1 mole of ester and say we take 10 moles of water, obviously water will be in excess amount. Okay. So when water is in excess amount, if this reacts, some the almost 10 moles would remain back in the solution. So when you are hydrolyzing a substance, okay, so that would react, but the amount of water that is reacting would significantly not change much. Okay. So suppose this reaction was going to completion, so 0.1 minus 0.1, so this would have become 0 because reaction is going to completion. We will be left with 9.9 moles of water, which is practically same as that of 10. But because it is a reaction is never going to complete, so we will say that some x portion has reacted. Now we know that x has to be smaller than 0.1. So if x amount of water has reacted, so it will be 10 minus x. So basically that x would be again be smaller than 0.1. So basically we would be left with almost 10 moles of H2O finally. So we say that whenever we are carrying out a reaction, say we are carrying out a hydrolysis, water will always be in excess amount. So basically water is present in excess amount. So a substance which is present in excess amount, its concentration change would be very small, and it's practically will say that the concentration of that substance remain constant. Okay. So from the rate equation it is appearing that it is a second order reaction, first order with respect to ester and first order with respect to water. But because the concentration of water here was not changing much, it was constant. So we will say that the concentration of water is constant. So we will write K into, that is rate constant into concentration of water, will be another constant because rate constant is a constant. concentration of water is not changing, it is constant. So the product of it will be a constant. So we can write this as K dash. So we'll write the rate as K dash into concentration of ester. Okay, so now this is the first order reaction with respect to ester. Now initially if you look at the rate law, because there were two reactants involved, so we will be thinking that its order is 2, but we are writing it as 1. So such kind of reactions are called as pseudo first order reactions. Reactions that have higher true order rate, okay, the higher the true order, the rate equation, the true rate equation was this, but we are writing it as K dash into concentration of ester because this is constant. Okay, so this is basically a first order reaction, but it was second order with respect to the rate law, the true rate law, but because the concentration of 1 is constant, it is taken in excess amount. So we are taking it as a constant and we are writing this as a first order equation. So this is called as a pseudo first order reaction. So the hydrolysis of ester is a pseudo first order reaction. Similarly, if you take, so hydrolysis of ester is a pseudo first order reaction in acidic medium, okay, because in basic medium the mechanism changes. So you need to remember that it is acidic medium, it is pseudo first order. And hydrolysis of sucrose in acidic medium is again a pseudo first order reaction. Okay, so what we are saying that whenever one of the reactant is in excess amount, so its concentration change is negligible, so its concentration is taken practically taken as a constant. So we absorb that quantity in the rate constant and we denote it by another rate constant, that is K dash. So this is basically the pseudo first order rate constant, okay, and K is basically the true rate constant, or you can write this as a second order rate constant. Okay. So I hope these terms are clear to you. So you can quickly write this. Okay. Now if we talk about the molecularity, because there are two reactants involved, so the molecularity should be equal to 2. So we say that the reactions having molecularity greater than equal to 2, okay, but the order of reaction is 1, they are called as pseudo unimolecular reaction. Okay. So basically if molecularity is 2, molecularity is always defined for a elementary reaction, that means two reactants are colliding with each other. Because it is elementary reaction, so order should also be 2. So basically if any reaction molecularity is greater than equal to 2, but the order of reaction is 1, it means that it is a pseudo unimolecular reaction. Okay. So I hope this is clear to everyone. Just write it down quickly. So we'll do some solving on this as well. Okay, so let us consider another example, that is pseudo bimolecular reaction. Now let us consider the hydrolysis of ester. Say suppose we are taking methyl ethanoate and we are hydrolyzing this in basic medium. Okay, so basically we are hydrolyzing this in a base. Okay, so we are taking water and along with it we are taking a basic medium we are taking. So this is basically will give us acid plus alcohol. Now this rate is equal to K into concentration of ester into concentration of water into concentration of OH negative or the base. Okay. Now we know that water is the solvent, it would be present in excess amount, so its concentration would practically be constant. So K into concentration of water can be replaced by another constant which is K dash. So we can write this as this. Okay. So basically this was the true rate law indicating that the order with respect to each reactant is 1. So the overall order should be 3, but if you look at this, the order is coming out to be 2. So this is called as a pseudo bimolecular reaction or a pseudo second order reaction. okay, where K dash is equal to K into concentration of water. Okay, so K dash is the pseudo rate constant, pseudo second order rate constant, K will be the overall rate constant of the reaction. So we can calculate the value of K by dividing K dash by H2O. Okay, so I hope this is clear to everyone. So basically we will say that reactions in which molecularity is greater than equal to 3, the molecularity would be 3, but the order is 2, such reactions are called as pseudo bimolecular reactions. Okay, so basically whatever is taken in excess amount, water generally is taken in excess amount because it also behaves as a solvent. So the concentration of it remains practically constant and it is taken as a constant. So it is absorbed in the rate constant, okay, and the pseudo rate law is written according to it. Okay, so I hope you have written this. So the hydrolysis of ester in basic medium is a pseudo second order reaction. Hydrolysis of a ester in acidic medium is a pseudo first order reaction. Okay, so this is again a very small objective question that can be framed. Okay, so let us look at a question over here. The question says that the hydrolysis of methyl acetate in aqueous solution has been studied by titrating the liberated acetic acid against NaOH. The concentration of ester at different time is given to us. Show that it follows a pseudo first order reaction as the concentration of water remains nearly constant. We know that the concentration of water is, or the molarity of water is 55.56 molar. So that value has been given to us. The concentration of water is 55 molar. During the course of reaction, what is the value of K dash in the equation? So rate equation has been given to us. Okay, so what we'll do in this case? We'll say that, okay, because it is a pseudo first order reaction, so this would be Kt into is equal to 2.303 log of initial concentration upon the final concentration. Okay, so basically the rate of this reaction would be K into concentration of ester, because K dash has been given to you, into concentration of water. Okay, we can write this as K into concentration of ester, where K dash is K into concentration of water. Okay, so this is our first order equation. The rate constant of a pseudo first order reaction was K, so we are writing over here K. So we'll just find the value of K at different time. At time t is equal to 0 corresponds to A naught, at time t 30 minutes, so take time as 30 minutes, plug the value of 0.8004, you will get the value of rate constant. Then we will calculate the rate constant for 60 minutes, take time as 60. Okay, so you can calculate the value of K by putting 80 as 0.7538. Similarly for the 90 second, the value of K, if it comes out to be same in all the cases, it means that it is a pseudo first order reaction. So we will get the value of K from them. Now we will say that K dash is equals to K into concentration of water. Okay, so we will calculate the value of K from here. Okay, so we know that K dash is K into concentration of water. So we are finding out the value of K from here. So the value of K dash would be K into concentration of water. Okay, so I hope this is clear to everyone. Just have a look. You can take a snapshot of the question as well. Okay, I have written this incorrectly. K is basically K dash into concentration of water. So we have calculated K. So we know that K is equals to K dash into concentration of water. K dash would be K upon water. Okay. So concentration of water is always taken as 55.56. In this question you have been given 55. So these are basically subjective level question that will actually help you in understanding how do we exactly are finding out the rate. Okay. So now let us understand the hydrolysis of ester in acidic medium and how it is determined experimentally. Okay. So just we will write a hydrolysis reaction. So suppose we are having suppose we are having a methyl ethanoate and we are hydrolyzing this in acidic medium. Okay. So basically this reaction is catalyzed by H plus. So this would get converted into acetic acid plus we'll get methanol over here. Okay. So just let us write its stoichiometric calculation. At time t is equals to 0, let us suppose that A moles of ester was present, water was in excess, so we don't need to consider it. After say some time t, x amount of this reacted, so we are left with A minus x, we will form x amount of acetic acid, x amount of methanol. Okay. Now when we are analyzing this reaction, because one of the product formed is acetic acid is formed. So what we will do, we will periodically titrate the reaction mixture with a strong acid, with a strong base, because one of the product is acid and we know that acid can be estimated by titrating it with a base. So what we are doing, we are taking up a setup, we are mixing the ester, water and H plus, and we are allowing the reaction to happen. After every say 5 minutes, we are taking out some portion of the reaction mixture and we are titrating it with a base. So on titrating it with a base, we will come to know the amount of acid that is present at that time. So we will get to know the amount of acid present, or we will get to know the value of x. Okay. And at time t is equals to infinity, we know that this would get consumed completely. It is a pseudo first order reaction and we will get A amount of this, A amount of this. Okay. Now just remember, this reaction is catalyzed by acid. Okay. So say at, so basically we are saying that the reaction is monitored by titrating the reaction mixture by a base, let's say NaOH. Okay. So we will say that again this is acid base titration, so number of moles of base consumed will be equal to number of moles of acid. So basically, because the molarity of NaOH would be fixed, so we will directly say that the volume of NaOH will be proportional to the amount of acid. Okay. So we will say that if V0 is the volume of NaOH consumed at t is equals to 0, okay, and Vt is the volume of NaOH consumed at say time t, and V infinity is the volume of NaOH consumed at time t is equals to infinity. Okay. So we are having this data. Okay. So like at time t is equals to 0, whatever base we are adding, okay, at time t is equals to 0, whatever base we are adding, will it titrate anything or it will remain unreacted? Now because we know that there is an acid present, this reaction is catalyzed by acids. So the acids catalysis means that this is consumed and this is regenerated back. So we will say that in the entire reaction the amount of H plus remains same. Okay. So we will say that at time t is equals to 0, whatever base we are adding, it will consume the acid that is present in the reaction mixture or the reactant, that is H plus, because at time t is equals to 0 we are having only reactant and reactant have a acid which is H plus over here. So at time t is equals to 0, V0 would be proportional to the amount of H plus present. Okay, so whatever amount of H plus is present, it will be entirely consumed by the NaOH. So we will get the amount of H plus present by titrating the mixture at time t is equals to 0. Now at time t, when the reaction has proceeded, so what we know? We know that some portion of this would have reacted, some amount of acid would be formed. Along with this acid, H plus would also be present because it is a catalyst in this reaction. Okay. So acetic acid would be present and this H plus is also present. So we will say that Vt is proportional to the amount of acetic acid formed, okay, which is x in this case, plus the amount of H plus present because it is a catalyst. So at every stage of the reaction it is regenerated back and its amount remains same. So we'll say that the amount of acetic acid formed, that is X, is proportional to V naught minus an amount of H plus present was, amount of H plus present is Vt. Okay, so we'll say that the amount of acetic acid formed will be proportional to Vt minus amount of H plus present. Now we know that the amount of H plus present is proportional to V naught. So basically X will be proportional to Vt minus V naught. Okay, I hope this step is clear to everyone. Now V infinity means that at time t is equals to infinity, reaction has gone for completion. So the entire amount of acetic acid is formed. Now whatever would be the initial moles of ester, that has been converted into acetic acid. So we'll say that V at time t is equals to infinity, acetic acid is present and again H plus will be present because it was a catalyst. So we'll say that V infinity is equal, will be proportional to amount of acetic acid formed plus, which is A in this case, okay, plus amount of H plus. We know that amount of H plus is proportional to V naught. So we'll say that A is proportional to V infinity minus V naught. Okay. So I hope this is also clear to you. So basically we have got two expression, X proportional to V t minus V naught and A proportional to V infinity minus V naught. So we'll say that A minus X will be proportional to, A is V infinity minus V naught minus Vt plus V naught. So basically V naught will get cancel out. So we'll get V infinity minus Vt. Okay. So A minus X is proportional to this. Okay. So I hope this is clear to you. So we'll write the first order equation for this as well. So suppose I am writing the first order equation over here. So I will say that Kt. Now K will be the rate constant of the pseudo first order reaction. You have to understand this is the pseudo first order reaction rate constant. Okay, so this will be equal to 2.303 log of, okay, what has been given to us? A is V infinity minus V naught upon log of A naught upon At. At is A minus X. A minus X is proportional to V infinity minus Vt. Okay, so this would be the expression of the rate first order rate equation, integrated rate equation for the hydrolysis of ester in terms of volume of base consumed. Okay, so you have to understand that this K is your pseudo first order rate constant. So basically rate of this reaction would be K into concentration of ester into concentration of water. Okay, so basically rate is K into concentration of ester. So K dash is basically, K is basically K dash into concentration of water. For the true rate constant of this reaction, what we have to do, we know that K dash will be equal to K into concentration of water, which is 55.56 molar. Okay, so just write it down quickly. I hope this is clear to everyone. Okay, so again question will come like this: V naught has been given to us, Vt is given to us. At different time interval, V infinity would be given to us. So at different time interval, we'll plug the value of Vt and the time we'll get the value of rate constant K. If the rate constant comes out to be same, it means that it is following the first order kinetics, and then we can calculate the actual rate constant of the reaction, which is that K upon concentration of water, which is 55.56. Okay, so I hope these steps are clear to you. This is actually very logical and basic understanding of stoichiometry and redox reactions and acid base titrations. Okay, so if you have not made the notes, you can take a snapshot of this. Now suppose when V naught is not given to us, so then what we'll do? Okay, so suppose when V naught is not given to us, so initial volume is not given. So we'll say that we know that Kt is equals to 2.303 log of C naught upon Ct. Okay, suppose we are finding the rate constant at time t1, so I can write this as C naught upon C t1. At time t2, I can write the equation as 2.303 log of C naught upon C t2 will be equal to K into T2. So, I will just subtract these two expressions. So, I will write this as K T1 minus T2 equals to 2.303 log of C naught by C T2 minus log of C naught C T1. Now, we can use the logarithm rule that log of y by x is log of y minus log of x. So, this will be log C naught minus log of C T2 minus log of C naught plus log of C T1. So, log C naught would get cancelled out. So, we will get 2.303 log of C T1 upon C T2. Okay. So, knowing the value of T1, T2 and the concentration at T1 and T2, we can calculate the value of rate constant. Again, this is the pseudo rate constant, okay, pseudo first order rate constant. So, we can write this expression also as K T1 minus T2 is equals to 2.303 log of C T1 would be V infinity minus V T1 divided by V infinity minus V T2. Okay, so, we do not know the value of V naught, only through the value of T1, V T1 and V T2, the volume of base at time T1 and time T2 and the volume of base at time t is equals to infinity, we can calculate the value of the rate constant. Okay. So, write it quickly. Okay, so, this is how the hydrolysis of ester in acidic medium is estimated by the titration of a base. Okay. So, again I have already discussed such kind of question. So, basically you have been given data to you. Okay. So, we have not been given V naught, we have been given only Vt. Okay. So, we will just use this expression, we know the value of V infinity, we know the value of V. Suppose this is the time T1, this is the time T2, we can calculate. Okay. So, I hope this is clear to everyone. So, we will calculate the rate constant for different time interval and we will get it as same. So, we will say that it is a first order reaction. Okay. So, now let us consider the inversion of cane sugar. So, this is again a very important concept. So, suppose we are having sucrose. Sucrose is basically C12H22O11. Okay. Now, when you hydrolyze this in acidic medium, we get a molecule of glucose and a molecule of fructose. Okay. For all those who are not used to these reactions, reactions will be given to you in the paper, so you do not have to worry about it. Anyways, we are going to discuss these reactions when we are doing organic. Okay. So, basically inversion of cane sugar was studied through their optical rotation. Okay. Now, you might have studied about the optical rotation in the optical activity chapter, optical isomerism. If not, like let us just follow the process. When we will do the isomerism, we will come to understand about it. So, let us say that at time t is equals to 0, the amount of sucrose was A, after say some time t, the amount was A minus x, after say time t is equals to infinity, this has completely reacted. So, this formed after would be this. Okay. Now, let R1 be the observed rotation of, okay, so this is the observed rotation of sucrose. Okay, this is defined per mole. Okay, so this is defined per mole. So, R1 is the observed rotation of sucrose, R2 is the observed rotation of say glucose and R3 is the observed rotation of fructose. Okay. So, they are all defined per mole. So, if 1 mole will have R1 rotation, 2 mole will have 2 R1 mole of 2 R1 rotation. Okay. So, what we are doing, we are monitoring the overall optical rotation. We know that the optically active compound rotate the plane of plane polarized light. So, at time t is equals to 0, only sucrose is present. Sucrose basically rotates the light in the clockwise direction. So, basically its optical rotation is plus 66. Okay. When it hydrolyzes, so glucose is having a rotation of plus 52.7 degree, fructose is having minus 92 degree, okay, and sucrose we know it's 66 degree. So this is basically R1 is 66, R2 is 52.7, R3 is basically minus 92.7. That data will be given to you, you don't have to remember anything. So we'll say that initially the optical rotation was clockwise. When we are hydrolyzing, some amount of this would be formed. Depending upon the moles that has reacted, we can decide the overall rotation, okay, because at time t is equals to t, the rotation will be due to this plus this plus this, because all the three molecules will rotate the light, okay, and at time t is equals to infinity, because entire amount of sucrose had changed into glucose and fructose, so the rotation would be because of these two compounds, okay. So say at time t is equals to 0, okay, we'll say that the optical rotation is R0. R0 is basically the optical rotation at time t is equals to 0. This will be proportional to, okay, the amount of rotation that sucrose is carrying out. So basically its mole is A and the observed rotation is R1, so it will be A into R1, okay, because this was defined per mole. Say after time t, the optical rotation would be due to sucrose, glucose as well as fructose, because all of them are capable of rotating the light. So the rotation of this would be A minus X moles of this into R1 plus moles of glucose, that is X, into its optical rotation, that is R2. Similarly, moles of fructose into its rotation, that is R3. Okay, so we can write RT as proportional to A R1 plus X R2 plus R3 minus R1. Okay. Now we know that AR1 is proportional to R0, so we can keep it over here. So we will write this as RT minus R0 is proportional to X R2 plus R3 minus R1. Now we know that the value of R2, R3 and R1, they are constant. So basically everything is constant. So I will say that X is proportional to RT minus R0, where RT is the optical rotation at time t and R0 is the optical rotation at time t is equals to 0. Okay. So let us analyze finally at time t is equals to infinity. Now we know that at time t is equals to infinity, only thing left would be glucose and fructose. So the rotation would be due to glucose and fructose. Rotation is R2 for glucose, R3 for fructose, because A moles have been formed. So R infinity, that is optical rotation of the solution after time t is equals to infinity, would be proportional to A into R3, that is rotation of fructose, plus A into optical rotation of glucose. Okay. So I can write R infinity as proportional to, okay, so I will just, what I will do is I will just subtract R0 from this. So I will get R infinity minus R0 will be proportional to A, I take as common, R3 plus R2 minus R1. Again this is a constant, okay, because they have a constant value. So we will say that A is proportional to, I can clearly say that A is proportional to R infinity minus R0. Okay, we have tried to bring the same factors over here because it is a proportionality. So if the two things are same, okay, R2 plus R3 minus R1, they will have the same proportionality constant. So when we take the ratio, they will get cancelled out. So basically we are getting A as R infinity minus R0, X as RT minus R0. So A minus X would be, okay, so in this case I will write it in the center. Okay, so I will say that A is proportional to R infinity minus R0. So AT or A minus X would be proportional to, A was this, X was this. So this will be proportional to R infinity minus RT. Okay, because this is a pseudo first order reaction, we know that for a pseudo first order reaction, KT, this K is the rate constant for the pseudo first order reaction. For the actual reaction, we know that K would be, K dash would be K of this pseudo first order reaction divided by concentration of water, which is 55.56. So the KT would be equal to 2.303 log of R infinity minus R naught divided by R infinity minus RT. So we have derived the rate equation in terms of optical rotation. Okay, RT is the optical rotation at time t, R naught is the optical rotation at time t is equals to 0, R infinity is the optical rotation at time t is equals to infinity. Okay, so just write this quickly or have a snapshot. This is actually a very important derivation of the formula. So in case you are facing difficulty in understanding the derivations of these formula, you can directly learn these expressions. Okay, so if you look at it, okay, basically for ester it was KT was equal to 2.303 log of V infinity minus Vt upon V infinity minus, sorry, V infinity minus V naught upon V infinity minus Vt. Here also the expression after log is almost the same, only instead of volume, rotation has come, okay, optical rotation has come. So it is R infinity minus R naught upon R infinity minus RT, okay. So let us quickly do some questions on this, so we will get a better understanding of this. I hope you have written this off. Okay, so this says that a 20% solution of cane sugar having dextro rotation means it is rotating the light in the plane polarized light in the clockwise direction, of 34.5 inverted by 0.5 normal lactic acid at 2, okay, the value is missing there, at 298 Kelvin. The rotations determined are as follows. Show that the inversion is a unimolecular reaction. You can do the same thing, just we have to use this formula. Okay, R naught RT has been given to us. Okay, so basically R naught has been given to us, RT has been given, and R infinity has been given to us. Just you have to use the value. You have to take the sign as well. So this is plus, this is plus, this is plus. R infinity is minus 10.77. So just put there, you will get the value of same K, right. So this is again a first order reaction. So this is also called as a inversion reaction. Now why this is called as inversion? Because initially the optical rotation was plus. Plus means it is rotating the plane polarized light in the clockwise direction. Now when the entire reaction has happened, when the entire sucrose has converted into glucose and fructose, so basically this has disappeared. So we will get the optical rotation 52.7 by glucose and minus 92 by fructose. So overall it would be, if you add the two, overall it would be negative. So this would be rotating the compound in the anti-clockwise manner. So sucrose basically rotates the light in the clockwise manner, but when it is completely hydrolyzed, the optical rotation would become negative. So now the compound would rotate the light in the anti-clockwise manner. That is why it is called as inversion. Okay, that is why sucrose is called as a inverted sugar also. Okay. So let us look at this question, solve this question. We will solve two questions on this now. So basically there is a reaction, first order reaction, sucrose changing into glucose or fructose, takes place at 308 Kelvin in 0.5 normal HCl. At time 0 the initial rotation of the mixture is 32.4, so we know that R naught has been given to as 32.4 degree. After 10 minutes the total rotation RT is given to us as 28.8 degree. If the rotation of sucrose per mole, okay, is 85 degree, that of glucose is 7.4 and fructose is minus 86.04, calculate the half life time period. Okay. So if you look at this question, we will say that KT is equals to 2.303 log of R infinity minus R naught upon R infinity minus RT. Okay. So we know the value of R naught, we know the value of RT. Okay. R naught is basically 32.4 at time t is equals to 0, RT is basically 28.8, but we don't know the value of R infinity. Okay. So we know that this reaction is happening, sucrose is getting converted into glucose plus fructose Okay. So at time t is equals to 0, suppose this is A, x amount of this has reacted. So after time t it would be A minus x. After time t is equals to infinity, this would have completely reacted, it would form A and A. Okay. So basically I will say that we know the optical rotation of sucrose, it is given to us as 85 degree. Okay, sucrose is given to us as 85 degree. So we know that at time t is equals to 0, 85 into A would be proportional to 32.4. Okay, and also we know that at time t, okay, there are sucrose, glucose and fructose present. So A minus x into the rotation of sucrose was 85 plus x into, sorry, this is x into the optical rotation of glucose, that is 7.4. So plus 7.4 into x plus, okay, fructose is present, that is again x. So its rotation is minus 86 so minus 86.04 into x would be proportional to the optical rotation at that time is 28.8. So basically we are having these two equations. So from here I will get to know about A. Okay, so I will directly write 85A as 3.24. So I will get the value of x. So A I am knowing is proportional to 3.24 divided by 85. Okay, similarly I will, from this I will get x proportional to, we will get something. So we know the value of A, we know the x. So basically I can write this as Kt is equals to 2.303 log of A upon A minus x, because R infinity was not given to us. So we cannot use this equation. Okay. So basically we are solving it through the stoichiometry method. So we know the value of A, from this we will get to know the value of x, we will put the value of A and A minus x and time as 10 minutes, we will get the value of K. Okay. So I hope this is also clear to you. So this would be basically K, okay, and T half would be 0.693 upon this K. Okay. Because this is a first order reaction, pseudo first order reaction. Okay. So I hope this question is clear to you. Again a very good conceptual question, like on a go it seems that it is little difficult. Again just do it after the class, just do the calculations and get the answer. Okay. I will share the answer with you in the next class. Now let us look at this question. So in this question we have been given at time t is equals to 0, so R naught is given to us as 24.1, R t has been given to us as 46, R infinity has been given to us as minus 10.7. Okay. So basically this is a pseudo first order reaction, the values has been given. So every value has been given, that means we can find out the rate constant. So I will say that Kt is equals to 2.303 log of R infinity minus 10.7 minus R naught was 24.1 divided by R infinity minus RT. So I will get this. So time I know is basically 46 minutes. So I will put 46 over here. So I will get the value of rate constant. Okay. So now the question says, from the following values calculate the rate constant. I already calculated the rate constant and the time. This rate constant is basically rate constant for the pseudo first order reaction, and the time at which solution is optically inactive. Okay, so this is again a good question. Time at which the solution is optically inactive. Solution will be optically inactive when the value of RT becomes 0. Neither the mixture is rotating the light in clockwise manner, nor it is rotating in anti-clockwise manner. So this has become optically inactive. So we will directly use this value of K into time. This will be equal to 2.303 log of R infinity would remain same, which is minus 10.7 minus RT, R naught would be same, minus 24.1 divided by R infinity minus RT. Okay. RT we know is 0 now. Okay. So now we know the value of rate constant from the first data. So we can calculate time from here. Okay. So this is again a beautifully crafted question. I can consider this as a difficult level question. Question number 7, question number 8, both are a good difficult level question, but with a good understanding about, okay, the inversion of cane sugar, you will come to understand how these formulas are derived and how you are approaching these questions. Okay. Now let us solve this question. Now this question basically says that the oxidation of certain metal is found to obey the equation. Okay. Now some metal is oxidizing, so when it oxidizes, a thick oxide layer would be formed at its surface. Okay, that's why we say that if you keep certain metals in air, it get tarnished because a thick oxide layer is formed. Example is aluminum. So that thickness is given by x, that is given by x square equals to alpha t plus beta. Now alpha is your constant, beta is your constant, and t is the time. We have been said that what is the order of this reaction. Okay, now how we'll do this? Just think for a while. Basically, to determine the order, we need to know the rate law. For the rate law, we can derive a differential rate law. So just we'll do is differentiation with respect to time. Okay, so when we differentiate with respect to time, so this will change into 2x dx by dt. Okay, so this will be alpha, and this is the constant, so it will be 0. So I can write dx by dt as alpha upon 1 by 2x. Okay, so this I can write as 2 alpha x. Oh, sorry, what I am writing over here. So this is basically alpha upon 2x. Okay, so if you write minus dx by dt, it will be minus alpha upon 2x. Okay, so dx by dt, that would be your rate of formation of that thin oxide. Okay, thin film oxide. So basically this represents rate. So if you can clearly say, rate is proportional to, or this is a constant, so I can write this as k into x raised to power minus 1. So you can clearly say that order with respect to the thickness of the oxide is minus 1. Okay, again a very simple question, a very beautiful question. Just you have to differentiate, you will get the rate law and you will get the order. Okay, so I hope this is clear to everyone. So we'll just keep on solving 2 more questions. Basically, I also wanted to teach writing rate laws for complex reaction and steady state approximation. These are basically a difficult or a high level concepts which I will cover in the next class. Before that, just solve 2 more questions. Okay. So there is one question, which of the following statements for the order of reaction is not correct. Okay. So just see, that is saying that it is not correct. Order can be determined experimentally. True or false? It is true. Order can be determined through experiments only. So this is a true statement. Okay. So this is not an incorrect statement. The order of the reaction is equal to the sum of the power of the concentration terms in the differential rate law. This is again true. We say that rate is equals to k into concentration of, say, a raised to power x into concentration of b raised to power y. So we will say that the order with respect to a is x and the order with respect to b is y. So overall order is x plus y. So basically overall order is the sum of the power to which the concentration terms has been raised. So this is also a correct statement. So this is not incorrect. It is not affected by the stoichiometric coefficient of the reactants. Okay, order, so it is incorrect. Order of a reaction will be fixed. Okay, it will change only when we change the experimental conditions, when the mechanism changes. Okay, so this is also correct. The order cannot be fractional. Okay, so this is incorrect because order can be fractional. Okay, so I hope this is clear to everyone. Okay, similarly this was a, okay, I will do it in the next class. So you can just take a snapshot of this question. Again, this question seems to be a little big, but believe me, it is very conceptual and it can be solved just in 2 steps. Okay, whatever we have done till now, by understanding the volumetric analysis of the reactant, we can easily solve this question and we'll get the answer in just 2 steps. So just take a snapshot of this, solve this, we'll discuss in the next class when we come for the next session. So I hope you are following these lectures sincerely and you are putting extra effort on this topic and doing all the subjective level problem that has been given to you through the daily practice problem sheet as well as what is done in the class. So I hope and I sincerely pray that everyone out there is safe and maintaining a good hygiene at home and working very hard. Okay, so even at this difficult time, your education or your study should not stop, and we are here to assist you. Okay. So, this is Animesh signing off for now. We will catch up on the next lecture, and we will definitely have some more interesting session and some conceptual question solving. Just take a snapshot of this, okay, and solve it. We will discuss it in the next class. Thank you everyone.